Hi everyone, it's Elizabeth here. Today I want to review how to calculate measures of association in STATA. In a previous session, you learned how to calculate several measures of disease frequency, including risks, odds, and rates. We've been using the Framingham Heart Study data, and we learned that we can calculate either the rate or the risk of death as the outcome because we can assume that all members of our cohort were followed for death over a 24-year period. On the other hand, when we were examining coronary heart disease as the outcome, we said that it is not appropriate to calculate risks because some people may have died or dropped out of the study before they developed coronary heart disease. Therefore, we used incidence rates that only allow a person to contribute information when they're being followed and they're at risk of developing the outcome of interest. Now we want to take this one step further. We want to use these measures of disease frequency like risks, odds, and rates, and we want to calculate the association between an exposure and our outcome. We said that there's different types of measures of association. We can calculate difference measures like a risk difference or a rate difference. We can calculate ratio measures like an odds ratio, a rate ratio, or a risk ratio. And we can calculate attributable fractions. So let's go ahead and do that using our data on smoking and death and coronary heart disease in the Framingham Heart Study. We're going to start by examining the association between smoking and death with several different measures of association. And then, as we said, we can only use rates when we're looking at the association between smoking and coronary heart disease. So to get started, let's look at the association between smoking status at visit 1, or that cursed smoke 1 variable, and the outcome of death. So in STATA, open up the Framingham Heart Study dataset. Then we're going to go to Statistics, Epidemiology and Related, Tables for Epidemiologist, and Cohort Study Risk Ratio. Our case variable is going to be death, and our exposure variable is going to be cursed smoke 1. Also, go ahead and select the Options tab and click on the box for Report Odds Ratio to ask STATA to also provide an odds ratio with this data. Click OK. And as you may remember from the last session, we looked at the risk of death among smokers, and we said that it was the 788 cases out of the 2,108 smokers gave us a risk of 0.36. And then among the non-smokers, the risk of death was 762 cases out of the 2,253 non-smokers, leading to a risk of 0.34. And again, now we can take this one step further. We have these measures of disease frequency, we have these risks, and now we want the measure of association between the risk of death in the smokers compared to the risk of the death in the non-smokers. And STATA provides two different values. It gives you your risk difference of 0.023 and our risk ratio of 1.07. And as you'll recall, our risk difference is the risk in the exposed minus the risk in the unexposed. So the 0.36 minus the 0.34 gave us a value of 0.023. So there was a 2.3% excess risk of death among smokers compared to non-smokers over the 24 years of follow-up. An alternative estimate would be the risk ratio, and we take the risk in the exposed divided by the risk in the unexposed, yielding an estimate of 1.07. This is saying that smokers had 1.07 times the risk of death compared to non-smokers over the 24 years of follow-up. The next thing that STATA provides is the attributable fraction among the exposed and the attributable fraction in the total population. And we've already calculated these values in lecture, but let's just remember how to get from this table of values to these estimates of the attributable fraction. The attributable fraction among the exposed was the risk ratio minus 1 divided by the risk ratio. 1.07 minus 1 divided by 1.07 yielded an estimate of 0.065. This can be interpreted as saying that 6.5% of the risk of deaths among the smokers can be attributed to smoking. For the attributable fraction among the total population, we first need to calculate the prevalence of exposure in our population. The prevalence of exposure in our population is the total number of smokers divided by the total population. So it's going to be the 2181 divided by the 4,434 people in our sample. So our prevalence of exposure is going to be 0.49, and then we can now plug that into our formula for the attributable fraction among the total population, and 0.49 times 1.07 minus 1 divided by 1 plus 0.49 times 1.07 minus 1 gives us a result of 0.033. So 3.3% of the risk of deaths in the total population can be attributed to smoking. And we had asked STATA to also provide an odds ratio, and here we get an estimate of 1.11. The disease odds ratio is the odds of death among the smokers divided by the odds of death among the non-smokers. And as you will remember, an odds is simply the risk divided by 1 minus the risk. So it's the risk of death among the smokers divided by 1 minus the risk of the death among smokers, divided by the odds of death among the non-smokers. So the risk of death among the non-smokers divided by 1 minus the risk of death among non-smokers. This leads to a value of 0.57 divided by 0.51, and we get a disease odds ratio of 1.11, stating that the odds of death is 1.11 times greater among smokers than non-smokers. Because of the symmetry of the odds ratio, instead of calculating the odds of death among smokers divided by the odds of death among non-smokers, we could also have calculated the odds of smoking among the people who died divided by the odds of smoking among the people who did not die. And if we carry that out, we can see that the odds of smoking among those who died is 1.03, and the odds of smoking among those who did not die is 0.93. And this leads to an exposure odds ratio of 1.11. This is saying that the odds of smoking is 1.11 times greater among those who died compared to those who did not die. And we'll see that this symmetry between the disease odds ratio and the exposure odds ratio becomes quite handy when we're conducting case control studies. And we'll discuss this further in later sessions. The next thing we want to do is calculate a rate for the association between smoking status at visit 1 and the rate of death. So let's return to STATA. We're going to go to Statistics, Epidemiology and Related, Tables for Epidemiologist, Incidence Rate Ratio. Our case variable is once again going to be death. Our exposed variable is once again going to be cur-smoke1. And because we're calculating rates, we now need to give a variable for person time, and that's going to be time death. So STATA tells us that among the people who were smokers, we had 788 cases among 44,440 person years, resulting in an incidence rate of 0.0177, or 0.0177 cases per person year, which is equivalent to saying 1.8 cases per 100 person years. Among the non-smokers, 762 deaths occurred among 46,675 person years, leading to an incidence rate of 0.016 cases per person year, which is equivalent to saying 1.6 cases per 100 person years. And we can use these two incidence rates to calculate an incidence rate difference or an incidence rate ratio. Our rate difference would be the rate in the exposed minus the rate in the unexposed, yielding an estimate of 1.4 cases per 1,000 person years. This would say that the rate of death is 1.4 cases per 1,000 person years higher among smokers than non-smokers. Our rate ratio would be the 0.0177 divided by the 0.0163, resulting in a rate ratio of 1.09. Stating that smokers had 1.09 times the rate of death compared to non-smokers. STATA also uses formulas to calculate the attributable fraction with rates. We didn't provide these formulas in lecture, but they're similar to the attributable fraction risk estimates. Here we can see that 7.9% of the death rate in smokers can be attributed to smoking, and 4% of the death rate in the total population can be attributed to smoking. The next thing we'd like to do is calculate rates for the association between smoking status at visit 1 and the rate of coronary heart disease. And again, we can calculate a rate difference or a rate ratio. In STATA, we're going to go back to Statistics, Epidemiology and Related, Tables for Epidemiologist, Incidence Rate Ratio. Our case variable is now going to be NECHD. Our exposure variable remains cur-smoke1, and our person time variable is now going to be switched to time CHD, because we want to censor people when they have CHD, not when they die. And we see here that among the smokers, there were 617 cases of any coronary heart disease among 39,636 person years, resulting in an incidence rate of 0.01556664. Among the non-smokers, there were 623 cases of any coronary heart disease among 41,288 person-years, resulting in an incidence rate of 0.015089, or 0.015 cases per person-year. And we can use these two estimates to come up with an incidence rate difference and an incidence rate ratio. Our incidence rate difference would be the 0.016 minus 0.015, resulting in a rate difference of 0.00048 cases per person-year, which is equivalent to saying 4.8 cases per 10,000 person-years. This can be interpreted as the rate of coronary heart disease is 4.8 cases per 10,000 person-years higher among smokers than non-smokers. Our rate ratio would be the 0.016 divided by the 0.015, resulting in an estimate of 1.03. Again, rate ratios are interpreted as a multiplicative effect, so the smokers had 1.03 times the rate of CHD compared to non-smokers. So in summary, we've now discussed several measures of disease frequency. We've looked at risks, which are appropriate when we can assume that there is no competing risks or loss to follow-up. We've used rates when we have person-time data to account for the fact that there can be competing risks and loss to follow-up. And we've looked at odds and the symmetry of using an odds ratio for the disease odds ratio and the exposure odds ratio, which will be extremely handy when we're looking at case control studies, and we'll discuss this further. We've looked at these different measures of association that can be calculated using these different measures of disease frequency. We discussed difference measures like a risk difference and a rate difference. We discussed ratio measures like an odds ratio, a risk ratio, and a rate ratio, and we discussed attributable fractions. And so far, in our data set, we've seen that smoking is associated with a higher risk, odds, and rate of death compared to non-smokers, and we saw that smokers had a higher rate of coronary heart disease compared to non-smokers. In subsequent sessions, we're now going to be looking into different issues of confounding and bias and effect measure modification. So we'll continue to pursue the association between smoking and coronary heart disease in this data set. See you soon.